Radiation. It's this invisible force that pretty much shapes our entire universe, right? From the crazy energy of stars millions of light years away to the medical tools that can literally save our lives. It's all around us, kind of like a constant silent hum. But how do you even begin to measure something you can't see or touch or feel? How do you get a handle on an energy that just passes through most things like they aren't even there? Well, the answer turns out to be both super elegant and incredibly powerful, and it's all inside a simple chamber filled with gas. So today, we're going to do a really deep dive into the principles of these gas-filled detectors, and we're going to uncover the beautiful physics of how we make the invisible not just visible, but something we can actually measure. Okay, so to really get this, we need a roadmap. We're going to start with the main problem. How do you detect something you can't see? Then, we're going to zoom way in on the single most important part of this whole thing, that first spark of ionization. From there, we'll go on what I like to call the voltage journey, where we'll basically turn up the power and watch how the detector's behavior just completely changes. After that, we'll connect the physics to real-world stuff before wrapping it all up with a look at how we've really learned to master this incredible cascade effect. All right, let's jump right in. The main challenge is pretty simple, right? A particle of radiation zips through a space, but it doesn't leave any obvious trace. So how do we know it was ever there? And maybe more importantly, how much energy did it have? The solution is the gas-filled detector, and at its heart, it's really just a container of a specific gas with two electrodes inside, a positive one, the anode, and a negative one, the cathode. It's a beautifully simple setup that works on one incredibly powerful idea. Here it is, the whole concept in a nutshell. First, some radiation comes flying into the gas, and like a tiny wrecking ball, it knocks electrons off the gas molecules it hits. Second, we apply a voltage to those two electrodes, which creates an electric field all through the gas. Third, this field acts like a powerful sorting machine, pulling the new negative electrons one way and the new positive gas molecules the other. We collect them, and that movement of charge is a tiny electrical current. And finally, and this is the magic part, the size of that current tells us a story. It tells us about the radiation that started the whole thing. Everything we talk about from here on out builds on this one core idea. You know, everything in these detectors, from the simplest little measurement to the most insane avalanche, it all starts with one single fundamental event: ionization. To get how these things work, we have to understand the ion pair. It's the basic unit of information we're trying to count. You can think of it like the footprint that the invisible particle leaves behind in the gas. So what is an ion pair exactly? Okay, imagine a neutral gas molecule, just chillin', perfectly balanced with all its electrons. Now a particle of radiation, this little focused bullet of energy, comes and smashes into it. The collision is so energetic that it knocks one of the molecule's electrons clean off. So now you've got two things that weren't there before: the free, negatively charged electron, which is now zipping around, and the original molecule, which is now missing an electron, leaving it with a positive charge. That pair, the heavy positive ion and the zippy little negative electron, that's our ion pair. Let's walk through this step by step. So radiation enters the chamber. As it travels, it doesn't just create one ion pair. It creates thousands of them, leaving this trail of charged particles behind it. Now, we turn on that voltage, creating the electric field. This field acts like a super strong sorting magnet. All those light, nimble little electrons get immediately yanked towards the positive electrode, the anode. At the same time, all the heavy, slow-moving positive ions get pulled towards the negative electrode, the cathode. This movement of charge, well, that is an electric current, and we can measure it. Okay, this is where our story gets really interesting. So we have our ion pairs, and we know an electric field can collect them. But what happens if we start to slowly turn up the dial on that voltage? What happens when we make that electric field stronger and stronger and stronger? Well, it turns out that by just changing this one thing, we can make the detector act in completely different ways. It's like we unlock a whole toolbox of scientific instruments from just one device. So let the journey begin. All right, let's start with the dial turned way down. At really low voltages, the electric field is super weak. It's like a gentle breeze trying to separate our positive ion and our negative electron. But see, they're naturally attracted to each other, so the weak field just isn't strong enough to pull them apart fast enough. And what happens? A lot of them just find each other again, snap back together, and become a neutral molecule. And poof, the signal is lost before we can even measure it. This is called the recombination region, and for what we're trying to do, it's not very useful at all. Now let's turn up that voltage, say into the 50 to 300 volt range.
All of a sudden, the electric field is strong, it's fast. It pulls every single ion pair apart and just sweeps them to the electrodes before they have any chance to recombine. We are now collecting 100% of the primary ion pairs, that is, every single one created by the original radiation. Now, the key word on this slide is plateaus. If we crank the voltage a little more in this region, the current doesn't go up, it stays flat. It's saturated. Why? Well, think about it. We're already collecting everything. You can't collect more than 100%, right? And that stability makes this saturation region incredibly useful for making precise measurements.
So the crucial takeaway here is that in this saturation region, the current we measure is a direct, honest count of how much ionization happened at the very beginning. And different kinds of radiation ionize differently. A big, heavy alpha particle is like a bowling ball crashing through pins. It just plows through the gas, creating this thick, dense trail of ion pairs, which gives us a big, strong current. But a smaller beta particle or a gamma ray, that's more like a BB gun pellet. It creates way fewer ion pairs, which means a much weaker current. And just like that, a detector in this region can tell the difference between types of radiation, just based on the size of the signal. Pretty cool. Let's keep turning that voltage dial up. Now something new and kind of amazing starts to happen. The electric field gets so strong that those primary electrons, as they're racing towards the anode, they pick up a ton of speed and energy. They move so fast that when they finally do hit another neutral gas molecule, bam! They hit it hard enough to knock another electron off. This is secondary ionization. The one original electron just created a whole new ion pair. We've just amplified our signal. And the scale of this amplification is just wild. A single electron from that one original particle of radiation can now trigger this little controlled cascade. That electron creates another, those two create more, and so on and so on. By the time this little storm hits the anode, what started as one electron has become a pulse of up to 1,000,000 electrons. This gas amplification takes a tiny, hard-to-measure signal and multiplies it into something our electronics can easily see. But the real beauty here is that the final signal is still proportional to the first one. So an alpha particle that made 10,000 primary electrons will still create a way bigger final pulse than a beta particle that only made 100. Both signals just get bigger. We keep cranking that voltage dial higher and higher. The amplification gets more and more extreme. And after a little unstable patch, we arrive at something truly dramatic, the Geiger region. In this region, the electric field is so intense that the whole idea of proportionality just gets thrown out the window. It doesn't matter anymore if the first event was a tiny gamma ray making one ion pair or a massive alpha particle making thousands. The pulse that comes out is exactly the same size, a huge, single, all-or-nothing spike. The physics here is best summed up by this quote from the source material. This signal is produced by an avalanche of interactions. That's the perfect word for it. It's not a controlled multiplication anymore, like in the proportional region. Nope. This is an explosive, runaway chain reaction that basically takes over the entire detector for a split second. A single ionization event, just one electron being set free, is all it takes to trigger it. It's like one tiny pebble starting a massive landslide. Okay, let's break down how this incredible avalanche actually happens. First, an electron, which has been super accelerated by that extreme voltage, slams into the anode. This impact is so energetic, it gives off a flash of ultraviolet light. And here's the kicker. This UV light shoots out in all directions, hitting other gas molecules way far away from where this started, and it ionizes them. This creates even more free electrons, and guess what they do? They rush to the anode, create more UV light, which creates more electrons. The whole process just spreads like wildfire down the entire anode wire, completely engulfing it in a cascade of charge. Just look at that number. Remember in the proportional region we were impressed with an amplification of 1,000,000? Well, here in the Geiger region, it can be as high as 10 billion. A single initial ion pair results in a cascade of 10 billion electrons hitting the anode. This creates this huge, unmistakable electrical pulse that's super easy to detect. It's the ultimate in sensitivity. But the trade-off is huge. We've lost all the information about the energy of the original particle. The detector just screams, "Yes, something was here." It can't tell you what it was, but it's absolutely 100% certain that it happened. So, we have these three really distinct, useful behaviors, all from just tweaking the voltage. So how does this actually translate to the real world? This is where we match the region to the job. Different scientific problems or medical needs require detectors that are built specifically to operate in one of these voltage zones. And this table just lays it all out perfectly. If you want to accurately measure the total energy, the dose, from a strong radiation source, you need that stable, honest signal from the saturation region. So you use an ionization chamber, like the dose calibrators that make sure cancer patients get the exact right amount of radiation. If you need to not only count particles, but also figure out their energy or what type they are, you need that controlled proportional amplification. So you use a proportional counter, perfect for a lab trying to identify some unknown radioactive sample. And if you just need to know if any radiation is around with the best sensitivity possible, you use a Geiger-Müller counter, running in that all-or-nothing avalanche mode to find even the tiniest trace of contamination. So let's just take a second and reflect on the journey we've taken. We started with this single, almost imperceptible event, an invisible particle knocking a single electron off an atom. And we've seen how, by carefully using a single physical principle, the electric field, we can turn that one little spark into a powerful, meaningful, and totally measurable signal. The big takeaway from this whole explainer is really about control. The elegance of the gas-filled detector is its amazing versatility. By just adjusting one knob, the voltage, we get to decide what the detector's job is. We can choose for it to be like a meticulous bookkeeper, carefully counting up the exact energy in the saturation region. We can make it a skilled analyst, amplifying signals to figure out what particles we're looking at in the proportional region. Or we can make it a hypersensitive watchdog, using the Geiger avalanche to sound the alarm for any radiation, no matter how weak. The journey from one single ion pair to a 10 billion electron avalanche, it's just a stunning example of human ingenuity. We took a fundamental interaction of the universe, and just by mastering a single force, we learned how to turn a whisper into a roar. It's a powerful reminder that the universe is just full of secrets, hiding in plain sight. And it really makes you wonder, doesn't it? What other invisible forces, what other hidden parts of our world are just waiting for us to find the right way to listen?